Hello, students. So, in our last screencast, we'd wrapped up vision and understanding how it worked. So, I thought you could take a moment and see if you can just identify the different structures labeled 1 through 5 here. So, why don't you hit pause, take a moment, see how you do, and on the count of three, I'm going to click the slide. 1, 2, 3. Here we go. Did you pause? I hope you paused. Do it for real. Okay, but here's the answers. Um, so take a look at that, and then if there's any you missed, maybe go back and review. So this screencast is all about hearing. So the goal of hearing is to convert a sound wave, or to get a sound wave to reach what are called hair cells in the cochlea of the inner ear. So that's kind of a lot. Let's sort of break it down a little bit here. So first of all, what is a sound wave? A sound wave is simply a vibration of air. So when I speak, if I put my hand in front of me, ha, ha, I can feel like air coming out onto my hand. And that vibration of air is all a sound wave is. Maybe you've been to a dance and you've stood by those big, ginormous speakers and the bass is like doof, 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 thumping, and you can like feel your whole body like getting pulsed by that vibration of air. Even the speakers themselves, the old school ones, kind of go boom, 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 and pumping that air. So that's all a sound wave is. And so basically, when that sound wave is kind of like moving across like this, it has to come in and enter our ears. And so it's going to travel through our ear to this purple thing called a cochlea. And then inside that cochlea, if we kind of uncoil it and look inside, there are what are called these little hair cells. And when those hair cells wiggle, they fire an action potential. So they are mechanoreceptors, and the physical movement causes them to fire an action potential. So that's kind of the gist of how the ear works. This vibration of air has to be transmitted into the depths of the ear to make these little hair cells wiggle. So let's look at the details. We're going to start with the outer ear. And the most obvious structure is what you probably think of as your ear, which is this right here. That is called the pinna. And its job is to funnel sound waves into the ear. So as those sound waves are moving, your pinna sort of collects those like a radar dish and kind of funnels them down this way. And we may not appreciate our pinna very much, but if you think about when you're having a hard time hearing somebody, what do? You're like, huh? And you kind of expand the range of your pinna. Or you might think of your dog. If your dog hears something in the distance, its ears might, as it tries to figure out where that is. So that's the pinna. It's going to filter the air down the auditory canal. And the auditory canal is just this tunnel, and it's going to funnel the sound wave to what's called the tympanic membrane. The auditory canal is kind of like the Q-tip zone. So even though Q-tips on the packaging say don't put these inside your ear, everyone in society does it anyway. It's like our nation's great lie. This is where the Q-tip is going into. And the reason why, by the way, they say don't put Q-tips in your ear is because you risk puncturing this tympanic membrane. That tympanic membrane is your eardrum. And when the sound wave hits that eardrum, it's a very thin thing, it actually will vibrate. So this is our first sort of conversion of energy here. That movement of air is converted into a vibration of the eardrum, the tympanic membrane, when it's struck. So at this point, we've converted the movement of air into a vibration of the eardrum. Okay, that brings us to the middle ear. 2 more letters and we're in Middle Earth, by the way, for you Lord of the Rings fans. Inside the middle ear are 3 what are called ossicles. The ossicles are these tiny bones. They're called the malleus, incus, and stapes. The shorthand or the common names for those are hammer, anvil, and stirrup. And these are absolutely tiny. I have a little case. It's maybe 2 inches long by 1 inch high. And in that little tiny case easily contains all 3 of these bones. And they kind of look like a hammer, an anvil, and a stirrup. And so that's why they're named that way. So when this tympanic membrane vibrates, these bones vibrate right along with it. Okay, so now we've converted the energy of this sound wave into the movement of these 3 little bones. Now, when those bones move, they kind of bang against what is called the oval window. And the oval window is going to transmit the movement of those tiny ossicle bones into the vibration of fluid inside this cochlea. In other words, if this is the oval window, the I'll do it the other way. If this is the oval window, those ossicles are kind of banging into it as they vibrate. So then when they hit that thing, that causes the vibration of fluid inside the cochlea. It's kind of like in Jurassic Park when they show the puddle and T-Rex is on the way and the water in the puddle is kind of like. So that's what's happening when these bones strike that oval window. The fluid in the cochlea is going like that. That brings us to the inner ear. And the cochlea is this coiled structure. This is the site of the mechanoreceptors that are going to actually help us to hear. So to understand this, we need to take this cochlea and uncoil it, chop it in half, and look at it end on. And if we look at it end on, we see this tiny area can be zoomed in, and we finally see those little hair cells. And essentially, when that fluid is vibrating, that causes this what's called basilar membrane to vibrate as well, which then wiggles the hair cells against that tectorial membrane. And the wiggling of the hair cell against that upper layer is what actually causes them to fire an action potential. So that is fairly complicated, but there's a lot of parts there, but really it's just converting energy from one form to another. We start with this movement of air, the sound wave. That is converted into the vibration of the tympanic membrane. That is converted into the movement of these ossicles. That is converted into the movement of fluid in this cochlea. And that movement of fluid is converted into the movement of these hair cells, which then triggers the sound. So, what parts of the brain are involved in processing hearing? As you might expect, the signal goes to that thalamus once again, and then it goes to the temporal lobe, which processes hearing. So that's pretty much it for the mechanics of hearing. There's a really good animation that I just covered up with that little pull-up menu, but I would really encourage you to pull up the slideshow and watch the animation because it kind of shows how different tones will cause different parts of this basilar membrane to vibrate. And so, high-pitched tones will cause one part of the basilar membrane to vibrate, stimulating one set of hair cells, but low-pitched tones stimulate a different part of this basilar membrane, triggering different sets of hair cells. And so this video kind of shows an animation of this while playing a very complicated song with lots of highs and notes and low notes. You just kind of visualize how that works. So I think that's definitely worth pulling up. Problems with hearing. So tinnitus, this is one that you all need to be aware of. Your generation is expected to experience tinnitus at rates unheard of in the history of humanity. What is tinnitus? It's a ringing in the ears. So basically, while you're hanging out, having a conversation, in the background there's this that kind of covers over everything that you're trying to hear. So it obviously makes hearing difficult. It can be really annoying. And it's kind of this constant thing. And what's happening is hair cells become damaged. And when they're damaged, they kind of fire random signals. And those random signals are processed by the brain as ringing. And so what causes the damage to the hair cells? Well, there's a couple things. One, rock concerts. We know that the volume at a typical rock concert is too loud to be safe. It's just too loud. And so cool kids, when they go to rock concerts, wear earplugs. Wear your earplugs, children. But yeah, if you're going to a lot of rock concerts, that for sure can do it. Soldiers in a war, if they're near an explosion, that could be like instant tinnitus, one shot, and the damage is, the sound is loud enough that can just cause tinnitus right there. So that's another common group. But the big one for, I think, a lot of kids your age are the headphones. You put your little earbuds in your ear, and you like to listen to your music, so you turn up the volume. You're not really thinking about it much. And what you don't realize is that volume, that sound is just being funneled right into your ear. Those hair cells are like, and that's a lot. And then you go in the hallway and you're walking down the hallway and people are talking and making noise and you can't hear your music. So you're like, I know, I'll turn up the volume. In the 80s, we would turn up the volume like this, it was like a very satisfying crank. Now you have to be like, push the button over and over. It's really annoying. But you turn up your volume so you can hear the music better, but then that puts even more pressure on your hair cells. So earbuds earbuds are really not the best. Those old 80s ones, like, I don't know if you've ever seen like foam, the like foam things that kind of sit over your head with a little, like, it's like you're wearing a headband. Um, those are kind of obnoxious because the sound goes everywhere, and so everyone else in the world can hear what you're listening to. But the nice thing about them is it's radiating that sound in all directions, so not as much was going into your ear. And I remember my dad had a rule that said, if you're going to listen to headphones, it has to be at a volume that I can't hear it. And that's probably a good rule. So if I were you, I'd ditch the earbuds. I've had more than one student during this, when hearing about this, say, wait, is that why my ears are ringing all the time? Um, and then there's this moment of, oh, good, what? And a couple of like two students have come back and said, yeah, I was diagnosed with tinnitus. So yeah, just better to avoid, because there's really not much to be done about it once you're affected by it. I want to talk about one more set of structures in the ear. These aren't involved in hearing, but they're just kind of good to know about anyway. So you might wonder, why do my ears pop on an airplane? Well, that has to do with what's called the auditory tube, also called the eustachian tube. Its job is to equalize pressure between the middle ear here and the outer ear. This tube connects to the throat. So when you go up in an airplane, the pressure goes down as you go up in the sky, and all of a sudden the outer ear has a lower pressure than your inner ear, or your middle ear. And so the higher pressure in the middle ear pushes against that flimsy little tympanic membrane. It kind of bulges out, and that's what that ear popping sensation is. And what they tell you to do is swallow, chew gum, do, that kind of a thing. And what all these things have in common is they're running air past your throat. And by running that outside air past your throat, you're kind of giving this high pressure air an outlet to rebalance. When you descend in an airplane, it's the same thing, except now the pressure is getting higher in the outer ear, and then the eardrum kind of pops the other way. The other set of structures are semicircular canals. These are three rings. You can't really tell from this picture, but they're at 90-degree angles to each other. This is how you can detect your head's orientation in space. It's also called your vestibular sense. And it's crazy. It sounds like I'm making this up, but I swear I'm not. Inside these semicircular canals, you've got these little hair cells, just like in your ear, but they're in this kind of gelatinous, oozy fluid. And floating in that fluid are these little, they're basically like little limestone rocks. They're called otoliths, but essentially they're rocks. And if you bend your head forward, that slimy ooze kind of, moves down and drags the rocks and bends the hair cells and says, hey, your head has just changed position. So as you move your head, you're sort of moving those rocks around and bending hair cells, and that's how you know what orientation your head is in. Imagine if you spin around really, really fast. Well, those otoliths can't really settle, and what happens? You can't tell what your position is in space because the otoliths aren't settling. That's what causes dizziness. And then the other thing is motion sickness. Motion sickness is caused when there's a disconnect between what your eyes and what your semicircular canals are telling your brain about where you are in space. And the vestibular sense gets slower with age, and so that disconnect gets more and more the older you are, which is why old people tend not to enjoy rides. And I remember I was swinging with my daughter a year or two ago, and I started to get motion sickness. I'm like, are you kidding me? I'm that old already, but apparently I am. So that's it for hearing, and that's it for the senses. Thanks.